So in 6.4, we are looking at what is called the central limit theorem. You've already dealt with, in the past, we worked with the normal curve. Remember when I taught you guys how to use the normal distribution table? Some of you were using sheets instead. Some of you used the table. Well, that's going to come back into play today a little bit. But the standard deviation that we use is going to be fluctuated just a little bit. Okay, so the central limit theorem says for all samples of the same size n, with n being greater than 30, the sampling distribution of x can be approximated by a normal distribution with a mean of mu and a standard deviation. And this is a little bit hard to read right here. This says sigma over the square root of n. Now remember that sigma, this is your standard deviation. And n is your sample size. Okay, so the mean is still going to be what they provide you, but the standard deviation is going to change a little bit. So normally if we did something with the normal curve, we were just plugging that standard deviation into sheets, or we were using it to find a z-score to then look up on the normal distribution table. This time we have to take the standard deviation and just change it a little bit by dividing it by the square root of the sample size. Now, the reason for that is that we're not just going to be looking at one individual. So anytime we've dealt with the normal curve so far, we've been looking at like, what if a single person is randomly selected? You know, what's the probability that one person is above or below some value? This time they're going to be questions about like a group of people. So what if we choose 100 people or 10 people or whatever? Now 10 doesn't really fit this criteria because it does say the sample size has to be greater than 30, right? So really we're going to be looking at 30 or more people in our little groups. So if you look at kind of this breaks it down just a little bit with earthquakes. So on the left-hand side, this graph over here on the left is just saying it's a histogram of the depths of 1,392 earthquakes. And the histogram shows that the distribution is definitely not normal. But then if you look at the sample means, so they're taking like a sample of people and then finding the mean of those and plotting that graph. So this is a histogram on the right-hand side, a histogram of 100 sample means, and each of those samples has 50 measurements in it. Okay, so you can see that is clearly a little more normal. It's approximately normal as far as that distribution is concerned. So on the left-hand side, we have a histogram that's about, every little bar is about one earthquake measurement. On the right hand side, you have a histogram where every bar is representing 50 earthquake measurements. Okay, so that's the difference, and that's why we end up using central limit theorem, because as mentioned, the standard deviation ends up being divided by the square root of the sample size. So if we were just talking about a sample size of 1, we would just be dividing by the square root of 1, which is 1. But if we're talking about a larger group, then we have to divide by that sample size, and it changes our standard deviation a little bit. Okay, so original earthquake depths have a skewed distribution, but when we collect samples and compute their means, these sample means have a distribution that is normal. So if we're doing the central limit theorem about our means, our population is going to have a mean of mu and a standard deviation of sigma. And then we're going to select simple random samples of the same size from our population, and this is how things are going to change. So our mean is still going to stay as mu, but our standard deviation is going to become the standard deviation divided by the square root of the sample size. If you still like to use the table, that's fine. You're going to have to deal with this formula right here. It's just saying that you're going to take your data, or you're going to take your mean, your data point minus your mean divided by our new version of the standard deviation, in which we just divide by the square root of the sample size. Okay, so we can do this when the population is normal or our sample size is greater than 30. If that's not the case, We can't do this. Okay, so of course they want you to check the requirements, right? Check to see that n is greater than 30, or if it comes from a normal distribution for the population, you can do this, and then they just break down those formulas for you again. Okay, so again, the mean is still going to be mu. The standard deviation is going to change. When we use the notation here, they do the mean sub x bar. So I'm going to rewrite this notation in my own handwriting so you can maybe understand it better. So they do the mean of the sample means is just equal to the mean of whatever they give you. Okay, so if they say the mean is this, that's going to be your mean. For the standard deviation, they're saying the standard deviation of the sample means is equal to the original standard deviation divided by the square root of the sample size. Okay, so I was just making note of this notation here. They just have a subscript on the mean and standard deviation. So if you see that in your homework, that's what they're talking about. Okay. All right, so here's an example problem that walks you through kind of the difference between the two scenarios. So the elevator in a car rental building in San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds, 27 passengers. Because 4,000 divided by 27 is 148, this converts to a mean passenger weight of 148 pounds when the elevator is full. We will assume a worst case scenario in which the elevator is filled with 27 adult males. Assume males have weights that are normally distributed with a mean of 189 and a standard deviation of 39. I'm going to actually make these two different color here. Okay, so find the probability that one randomly selected adult male has a weight greater than 148. Okay, so this goes back to the just normal distribution. We're just talking about one person here. So remember, we centered ourselves at the mean, which in this case is 189. And then there's a standard deviation of 39. So since this is just about one randomly selected adult male, I can do a sheets, hang on, let me put we want to know if it's greater than 148. So 148 is going to be somewhere over here. So 148, and we're looking for this area to the right because it said greater than. Okay, so this should be familiar. This is from like 6.2, I believe. Oh, that's nice. Hang on. Okay, that's better. You knew what I was trying to do. Okay, so if you remember when we put things into sheets or we look things up on the table, it always wants what's to the left. But we are looking for what's to the right, so I'm going to do 1 minus here. I'm going to do 1 minus norm dist. This is if I'm doing sheets, right? 1 minus norm dist. And they're going to ask you for the x value, which is 148. They're going to ask you for the mean, which is 189. They're going to ask you for the standard deviation, which is 39. And if it's cumulative, and it always is, so we're going to say true. Okay. So we're going to do 1 minus norm dist, 148, 189, 39, and true. And I think I actually have sheets on here. There we go. So I'll go ahead and do one of these for you, instead of switching back to my laptop screen. Okay, so I'm going to do equals 1 minus norm dist of 148, 189, 39, and true. Okay, so that area that I shaded should be 0.8534. Let's go with that. 0.8534. Okay. Now, I think there may be a couple of people that are sticking to the table, so I'm going to go ahead and make sure that we're still okay with that. So if I'm going to do the table, I need to find a z-score for that value of 148. So I'm going to do 148 minus the mean divided by the standard deviation. And get a z-score from that. I don't know where my calculator is, so I'll do my phone here. 148 minus 189 divided by 39 comes out to be negative 1.05. Okay, so that's the value I'm going to look up on those z tables. So let me find one here. Normal distribution table. I always use this first one here. So negative 0.105. So 0, 1, 2, 3, 4, 5. It's this value here, 0.14686. 0.14686. Okay, so if I looked this up on the table, I'm going to get 0.14686, but that's the area to the left, so I'm going to finish that off by doing 1 minus 0.14686, and that should give me the same answer-ish that I got before. So 1 minus 0.14686 gives you 0.85314. Okay, so you can tell it's just slightly different, but as mentioned before, sheets in the table, sheets is going to be more accurate because the table has rounded a little bit, and we rounded the z-score we got, so even the value we looked up on the table is rounded. Okay, so that's a problem you've seen before. That's nothing new, but the next piece of it is going to be a little bit different. So see how in part B it says, find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148. Now, 27 is not greater than 30, but if you look back in the problem, it does say that you can assume that they are normally distributed. So it is okay if we go ahead and use central limit theorem in this case, even though we have a sample size less than 30. Okay, and I think the most the easiest way to go ahead and start a problem like this is to just go ahead and reference what our mean and standard deviation are going to be. So mean of the sample in this case is still going to be what the mean was before, which was 189. The standard deviation of the sample, this is what we're going to do, our original standard deviation divided by the square root of the sample size. I don't know why I wrote 27 there, should have written n. Okay, and then I'll fill in the information. So our original standard deviation was 39, square root of our sample size, which is 27. Okay, so we're going to do 39 divided by the square root of 27, and I actually do want my calculator in this case. Hold on just a second. Okay, so I'm going to do 39 divided by the square root of 27. I have a calculator on my iPad. I don't know why I just did that. Hang on, it's right here. So 39 divided by the square root of 27 comes out to be 7.5. Okay, so 7.5. 7.5 is our new standard deviation. Okay, so that's what we're going to enter into sheets or look up, use to find the z-score to look up on the table. Okay, so we're still looking up to see a weight greater than 148. Our mean is still 189. Okay, we're still looking to the right. We want to see what's greater than 148. But instead of putting in 39 as my standard deviation, now I'm going to put in 7.5. So I can still use the same formula in sheets, norm dist, 148, 189. Instead of 39, now I'm going to put 7.5, but it's still true. Okay, and so then let's go figure out what that one is. Okay, so I'm going to do 1 minus norm dist of 148, 189, 7.5, and true. Okay, and I get 0.9999 repeating, so we're just going to say it's 1, because if we round to any reasonable decimal place, it's just going to be 1. Okay, so In this case, we get 1. Okay, so for those of you that are loyal to the table, show you what you need to do here. Okay, so we're still going to find a z-score. We're still going to do our value minus our mean. Now we're going to divide by our standard deviation. The nice thing is we've already done that. We've already taken our old standard deviation, divided it by our square root of our sample size, and we got 7.5. Ooh, sorry. So I'm just going to put 7.5 down here because that's my new standard deviation. Okay, so I'm going to do 148 minus 189 and divide that by 7.5. Okay, and I'm going to get negative 5.5. And this is the value I'm going to look up on the table. Okay, you can probably guess it's really not even on there. Okay, but if you looked up negative 5.5 on the table, it would definitely be 0, right? Because I can't go any higher than this, and these probabilities are getting smaller and smaller as we go. So we're just going to assume that it's 0, but remember we had to do 1 minus, right? So we're assuming that we got 0 and we looked it up on the table. So in our final step, we do 1 minus 0, and we're just going to get 1, just like we did right here. Okay, so all you have to do is calculate that new standard deviation if you have a sample size greater than 30, or they tell you that the population is normally distributed, and that is for when you're finding the probability of a sample. Okay, so you're not going to do that unless you see this right here. Find the probability of the sample of some amount. Okay. Otherwise, if it just says find the probability of 1, then you're going to treat it like it's a problem from like 6.2. Okay. Hopefully this is helpful. I will post these notes that I've written all over, so you have exactly what I've done here. So I'll throw them to you in an email, and I'll of course link you to this video, which is how you're going to see it. And then if you have any questions about the homework, please just let me know. I'll open that up for you. And if we need to discuss anything, happy to do so. Okay. See you guys later.